Okay, so as I said, I'm going to come from the Koopman side and give you a very brief overview of the general Koopman idea, and then that's going to somehow motivate the design and algorithms for the dynamic mode decomposition, and then I go into applications and see what it's actually good for. All right, so quick outline. As I said, I'm going to start with Koopman analysis. Very brief introduction, just the idea. You know, there could be a talk about Koopman all by itself. Then I'm going to go right into data decompositions in general, how to decompose data. We already saw from Scott one way of decomposing data. So I'm going to juxtapose that one to the dynamic mode decomposition, see what is in common and what is very specific to the dynamic mode decomposition. I'm going to talk about Koopman embeddings by dynamic modes, a robust amplitude algorithm to figure out your amplitudes from experimental data that may have some outliers or some noise and uncertainty in it. And then we're going to go through some applications for data-based feature extraction. I picked 3 applications for a very specific reason. And then I'm going to show you also some current developments and some exciting new directions that dynamic modes and Koopman theory are actually going at the moment. Okay, so Koopman analysis, a very brief introduction. Koopman analysis is a different way of looking at dynamical systems, very different from the Poincaré type of viewpoint that we learn in mathematics. So the Poincaré is very much state-based, state vector-based. We go for equilibrium solutions. We linearize around the equilibrium solutions. We look at the Jacobian. We look at the eigenvalues of the Jacobian. We do fixed point analysis and so on, bifurcation analysis. All of that one is in the Poincaré viewpoint. The Koopman viewpoint is doing it very differently. The Koopman viewpoint is trying to actually transform a dynamical system, a nonlinear dynamical system, through a nonlinear coordinate transformation into a dynamical system of observables that behave linearly. Okay? So if you want to write that down with a little bit more mathematics, we have an x dot is equal to fx, that's the nonlinear dynamical system, and then some magical transformation z with new coordinates phi of x gives us a linear dynamical system, z dot is equal to L times z. Okay, of course, then we have to figure out what that coordinate transformation is and what that coordination transformation actually is turning our nonlinear dynamical systems into. So the operator L has to be recovered just as well. Okay. Now, the way we want to do that is, of course, we want to do that from data. So we want to have just an observable phase space curve in Rn that observes our state and derivatives of the state. Sometimes the partial state, sometimes proxy variables of the state. We cannot always measure the entire state. And then out of that one, we're going to extract both the embedding, the phi, the coordinate transformation, and that linear operator in one shot. Okay, so that's mathematically what we're trying to do. So let me also go to the I'm going to switch between the continuous and the discrete one too. If we have data, of course, we most likely have a time discrete system. So we have xn plus 1 is f of xn. And then we're going to we introduce observables. So that is a function on our vector space. Okay, on our state space X, that we're going to observe in time. And then we're going to define on that observables that we have, okay, we define a propagation operator. So g of xn, okay, and g of f of xn, of course, f of xn is the n plus 1, the next snapshot that carries us over from one snapshot to the next. And if you look the observable at that next snapshot, the linear operation that gets us from one to the next snapshot in our observable space is defined as the Koopman operator. Okay. Now, this is the Koopman operator. So it looks like a little bit like a magical trick, but there's a big drawback on the whole thing. So this is again the two ways of looking at it. Here is the state vector xn. Here is our nonlinear dynamical system. That's the mapping to the xn plus 1, f to xn plus 2, and so on. So this would be the Poincaré way of looking at it as a time series. Okay? And right underneath there is what we map to in the observable space. So this is the observable that goes with xn. This is the observable that goes with xn plus 1, and this one with n plus 2. And the propagator from one to the next is actually linear. Okay. Now, as I said, this looks like a little bit of magic, but you have to realize that these GNs are actually functions. Okay, so they're infinite dimensional. They can be anything you want. They need to be rich enough such that the nonlinear dynamical system is representable by an equivalent linear system in a higher dimensional space. Okay, so we trade a nonlinear mapping in a smaller dimensional space by a linear mapping in a much, much bigger dimensional space. So we trade linearity for dimensionality. Okay, that's the Koopman idea. Okay, so we turn a finite dimensional nonlinear dynamical system into an infinite, theoretically infinite dimensional linear system. And then we just hope that infinite in that case is hopefully not infinite, but large enough and it cuts off, and then we're going to cover just as much. Okay? So let me give you two examples. They were inspired by Clancy-Rowley to somehow give you a little bit of an idea how that thing works. So let's say we have a following example. X dot is equal to mu times x1, and x2 dot is equal to lambda x2 minus x1 squared. Okay, that's definitely a nonlinear dynamical system. And now I'm going to introduce my observables. And the observables that I want to introduce, that I call y, is y1 is the same as x1, y2 is the same as x2, and then I introduce a third observable. So here we go with infinite dimensional. That one actually cuts off at 3 observables. And that one is y1 squared. Okay, sorry, it's at x1 squared here. Okay, I just use different y's to distinguish between the state and the observables. Okay, so these are known as reaction variables, or this is our Koopman embedding, the magical transformation into a different coordinate system. Because if you write down the differential equation for these 3 variables, the y1, the y2, and the y1 squared, this is what you get. ddt of our observable space now, that is 1 larger than the original system was, actually closes up and makes this one a linear system.
Is there something like a theorem for the upper bound if your dynamical system is polynomial?
Not that I know. Not that I know. Yeah. So this is a closed linear system. That means I don't need to augment that one to infinity to close it up. Okay. This one closes up after 3 observables, the 2 state variables, and then the square of the first one gives me a linear system, and this would be the Koopman operator propagating my 3 observables. Okay, so 3 was infinity in that case. We got lucky. So let's do the same thing on another system. That one is discrete in time now. That's the logistic map. Okay, almost the same one, beta xn, and then an xn squared. And let's be inspired by the previous one that looked at the equations, figured out that there is an x squared, or an x1 squared in our case, and use that one as an observable. Okay, so if you do the same trick here, yn is just the xn, and then we see an xn squared, so we introduce that one as our observable. If we do exactly the same thing, it doesn't close up, because if you write down the logistic map for yn squared, that one goes into yn cubed and the quartic term. Then you write down something for the quartic term and the cubic term. That one needs power of 5 and 6 and higher and higher. This thing is running away from you. Okay? Now, this choosing observables by powers, that one has been around just about as long as the Koopman idea has been around, and that one is known as Karman linearization. Okay? Didn't work in the 20s, still doesn't work today. We just got lucky the other time with our system. So this one actually is an infinite linear system because obviously the observables you should choose, or the observables you have to choose are infinite in this direction. They're not expressible or not simply expressible by powers. There's a way of expressing them by exponentials, but this system here just goes on forever. So this would be an example where introducing the powers as observables just doesn't close up the system. Okay.
What is more generic? Is this a generic case?
That's more a generic case. Yeah. Yeah. The other one was quite special. Yeah. Okay. So the question is, if this one has to succeed at all, the question is, how do we choose the infinite series of observables? How do we actually augment our state vectors by the proper observables such that the whole thing eventually closes up, or at least approximately closes up? Okay. The bad thing about that system also is this is actually turning into a quite nasty system too. Maybe Steve will talk about that in some of the next days. Okay. So, choosing the powers of the state vector in example 2, we basically, what we do is we outrun the span of the observable basis and closure is not reached. Okay? So we outrun the basis. That means if we have the linear and the quadratic basis, it needs the cubic basis. The cubic needs the quartic needs the quintic, and so on and so on. We just keep running away from our basis. So what do we do about that? Well, there is actually a basis that is a very natural basis for not running away from us. And that one is the invariant subspace. In other words, the eigenvectors of the Koopman operator. Okay? So the Koopman operator, acting on its eigenvectors, of course, just like any linear operator, is staying within the basis of the eigenvectors, just multiplying by a scalar. Okay? So if we express something in phi, then by applying the Koopman operator, by stepping our scheme forward in the observables, these things will always stay within the same basis. That's why we call eigenvectors the invariant subspace. It is invariant under action of the Koopman operator. Okay? So they do the magic trick. So that means if we express our observables in the Koopman eigenvector basis, and let's call them one phi times some coefficient psi, then every time I have an observable and I step that over k steps, I just multiply that one by k times the Koopman operator. Okay, k, every k pushes it over one time step from snapshot to snapshot in our observables. Okay, and that one is just lambda to the k times phi times psi. And that one enforces closure almost automatically, right? Because the eigenvectors fold back onto themselves. There's no running away of the basis. Okay? So with this general strategy here, the question now has been turned from figuring out the proper observables. We have figured them out now, but now we have to decide on how do we actually get these things out. Okay? So how do we compute the basis, the Koopman eigenvectors? Okay? We're going to link that one to a data matrix decomposition through time stepping. So I take my observables over k units. Okay? That's k to the k, the Koopman operator applied k times in a row to generate all the data matrices. This is my observable, just expressed as Koopman functions. And that one is Koopman eigenvectors times psi. That's the amplitudes in that basis of my observables. And lambda to the k is more or less doing the time stepping for me. Okay, that one is pushed. This is the only one that has a k power. So this must be responsible for getting from time step to time step to time step, generating all the snapshots. So if you write that one down as a data decomposition, just like Scott has done, so this is all the observables So this is, let's say, this one is space. Doesn't have to be, but let's just for simplicity say this is space. This is my time axis. Okay, so these are all my observables. This is the time axis. Every column is a different snapshot. For simplicity, equispaced in time. I can let that go later on, but for now, for the derivation, it's actually quite convenient. And then what we have over here is a triple decomposition, just like Scott had before. Okay, the first one is the structures. These are my Koopman eigenfunctions. The middle one are coefficients. That one is my spectrum or the amplitudes. And this part here, lambda to the k, is doing my time evolution. It's exactly the same thing that we did with the POD before the coffee break. Okay, so now a Koopman decomposition of observables is nothing more than a data decomposition of a data matrix. Matrix decomposition, a factorization into modal structures. So these are spatial structures. These are the amplitudes, and this is the dynamics. And at this point, the only thing that I prescribe is that the middle matrix, the B matrix with the amplitude, is diagonal. That makes it nice to break it apart into which structure has what dynamics. Okay, so they don't mingle up. They can be studied in isolation. All right, so now we reduce something that is, we really have a data-driven technique now, okay? Because these are the data, the observables of our data stacked in time, and this is our decomposition. These are the magical Koopman eigenvectors, okay, that we try to squeeze out of the data matrix. These are the amplitudes, and this is the dynamics. So if I just say A, B, and C and have a data matrix like this, just like Scott mentioned, this is not unique. I have to say something a little bit more. And having the middle matrix being diagonal is not sufficient. One more thing I need to say to nail down this decomposition and make it unique. Modulo some rotations, subspace rotations, okay? And this is where all these data decompositions come in. For example, if I make one more choice and say A has to have orthogonal columns, or A has to be unitary, either way, okay? That one is enough to uniquely define this decomposition as an SVD. And that's exactly like POD. Okay, so this is the SVD. If I make this choice, of course, there's many other choices that I can make. Okay, I can also say, I don't care what A is, I put my constraint on C. This is the dynamics, this is the temporal dynamics. And I want to have something where each timeline, so each row in here, is statistically independent of any other row. Okay? Then I do independent component analysis. That's another way of breaking it apart. Okay? It's totally up to you. Okay? And a third one, there's many, many other ones. If I say that B doesn't have to be strictly diagonal, but block diagonal, and C has to be maximally sparse, I do blind convolutional, blind compressive sensing. Okay, that's another way of breaking it apart. You can come up with anything else. One has to have low rank, the other one has to have sparse entries, and you get all these decompositions just percolate out of the same breaking apart of A, B, and C. Okay, now, which one do we take? Well, let's go back to our equation for the Koopman operation. So these are our observables. Okay, that one is in the D matrix encoded. This one will later on give us the phis. The phis will give us the modes. The size will be picked off of the diagonal of B, and lambda to the k will be here. Okay, so in our case, this is certainly a result. We should not say ahead of time what kind of properties they have. Diagonality is already enforced automatically. So what we do is we're going to go for the last final constraint is the shape of the C matrix. Okay? And the shape of the C matrix is given here, lambda to the k. So the shape of the C matrix looks exactly like this. 1, lambda 1, I don't know what lambda 1 is. Lambda 2 is lambda 1 squared. cubed, and so on, as I step along, right? This is the magic of using the eigenfunctions of the Koopman operator, and then the eigenvalues will just power out the more often I apply to step it from one time step to the next. Okay? So my C matrix has this shape. This is my final constraint that nails or should nail it down. So C is a Vandermonde matrix. This is what a Vandermonde matrix looks like. Okay, you probably have seen Vandermonde matrices from polynomial interpolation. Okay, you probably also remember that everybody warns you about Vandermonde matrices. They're notoriously ill-conditioned. Okay, and we'll work our way around that one. But at the moment, we have a decomposition of any rectangular matrix into another rectangular matrix, a diagonal one, and a Vandermonde matrix. Okay, so if you look that up, there is no decomposition like this, or at least not one you can pull off the shelf. So we have to work a little harder to get this. How do we compute that? This is what we want. Okay? So the critical observation here is Vandermonde matrices diagonalize companion matrices. Okay? That's something out of a linear algebra book, okay? Or a good linear algebra course if you had one. So what does that mean? If I have a diagonal matrix B here, and I add a Vandermonde matrix on both sides like a similarity transformation, I can, if I choose the Vandermonde matrix properly, I can turn that one into a companion matrix that has this shape. This is how a companion matrix looks like. It has zeros everywhere except at a subdiagonal of 1, and the last column is filled with coefficients. Okay? So there's a nice link between those two matrices. And it somehow makes sense also because this Vandermonde matrix really only has n entries. It's an n squared matrix, but it only has n matrix. All I need to give you is the second column. Okay? And then you can build it. The first one is always ones, and the other ones are powers of the first column. So the degree of dimensionality of a Vandermonde matrix is n, and so, of course, is a companion matrix. The only real degrees of freedom is the n's in the last column. Okay? So, now, let's continue up here. B times C, diagonal times Vandermonde, now can be written as K times C times K, right? I just bring C over to the other side, and then I replace the BC here by the CK. So now my decomposition looks like A times C times K. C is Vandermonde, K is companion. Doesn't look like we're going anywhere. We're just making things more and more complicated. Okay. Now, A is unknown at this point. C is unknown at this point, but I know the shape of it. K is unknown at this point, but I know the shape of it. The only thing that I know is D. A times C together, two unknowns may still make an unknown if I multiply it together. So I just call it one D prime. So now I have the data matrix that I do know, some matrix D prime that I don't know, or I think I don't know, and out of the K, I only know the shape of it. It has to be companion. But now let's look at the companion matrix. What do these ones do? These ones on the subdiagonal just shift columns. Okay? They just shift columns. So I said D prime, I don't know. I actually do know most of the D prime. It's the shifted version of the D. Okay? Because D prime times the K, at least the column part, that column shift part of D, is just reproducing what I have on the other side. So most of the D prime I know. It's reproduced columns. It's copied columns. That's what the ones do. And then the only thing is the last column in D has to be multiplied by the linear combination of all the ones in D prime. Okay? So what I need to do now is I have the data matrix here, and the D prime I get by taking the last column of D and expressing it as a linear combination of all the other ones before in D. That's nothing more than what the companion matrix does. So it looks like I don't know D prime. But by that trick of using a companion matrix, I actually got myself an algorithm to figure out what D prime is and what K is at the same time. Okay? That's how we do that. And it all came from a Vandermonde matrix to start with. Okay? So the way we do that is we express the last data snapshot as a linear combination of the previous snapshots in D. That gives us the ANs. We slap on the ANs in the last column, fill it up with ones on a subdiagonal. That gives us the K. And then if you want to, you can go back and transform it back and get the A, the B, and the C. And that's our decomposition. Okay? And that, in a nutshell, is the dynamic mode decomposition. So here it is, the algorithm. We consider a snapshot basis, and I'm going to introduce the notation V1 and N. 1 is sub and N is high. It's a superscript. And that one is the notation V1, first snapshot, and N is the last one. And I use it for equispaced. You see now why I use equispaced, because that makes the nice ones down a diagonal. It's a subdiagonal, sorry, of the companion matrix. Okay? All right, so let's just say I have a magical matrix A that is huge, that hits all my snapshots and transforms it over one time step. Okay? That's the Navier-Stokes code that does one time step, for example. Okay? If these are observables, of course, that's an approximation to the Koopman operator. And that one transfers everything one step over. So I have 2 to n plus 1. And then this is expressed in the snapshot sequence that I had previously, unchanged. Okay? And the S here is my companion matrix. Okay? So if you leave out the middle part here, this part here, then you say, this is my operator, high-dimensional operator A, that moves a bunch of snapshots over one time step. Okay? And expressed in that basis, if that one is rich enough to express all the action of A, it should be captured by the basis itself. And the way it is captured in the basis itself is that matrix S. So in essence, the action of A is expressed approximately by the action of S. Pre-action, post-action. Okay? And that's exactly, if you leave out the middle thing, that looks awfully close to an Arnoldi technique or Krylov subspace technique. Right? That's the idea of a Krylov subspace technique. We hit it with a big matrix A, and hopefully, often enough, we get the major dynamics of that matrix A out into a smaller matrix that is Hessenberg matrix, and then we get the eigenvalues of that one instead of the eigenvalues of the big ones. And hopefully we capture the big dynamics. It's the same idea. If you leave out the middle part, then this S should capture the main dynamics of the A. But we don't have A. Okay? So what we do is we cut out this part and just work with our data and still get the S of it out of the data. Not by decomposing A, but by how A acts on data. Okay? So we concentrate on this thing. So here again, if this is my first snapshot here, this is V2. That one appears in the second position of V1 to N plus to N. Right? The red one is in second position. The green one is in second position here. This is in third position there. I can assign that. And that one, of course, totally corresponds to the companion matrix. Okay? And the last one, of course, is nowhere to be found because that's the last one. Doesn't appear here, okay? Because it falls off the edge of the matrix. That way, we have to express it by whatever we have to do it with, and that one gives us the companion matrix. Okay? So, and as I said, for example, anything you want to know about the big matrix A that is somewhere encoded in our snapshot basis, everything you want to know about A, you can now ask about S. Okay? Eigenvalues, some of them, hopefully the important ones, will be captured by S. You can do resolvents, you can do SVDs, you can do whatever you want to. Any matrix function you want to evaluate, you evaluate on S, the little one, instead of the big one. Yeah. Yeah.
May I ask you to repeat how you compute A1, A2, and
By least squares, right? So
they just a linear combination of the other one?
yes, exactly. So I take the last snapshot, the n+1 snapshot. It's not in here, but I say the n+1 snapshot, the purple one here, is a linear combination of all the ones from 1 to n. And that's the coefficients to express the last snapshot by a linear combination of all the previous ones. Okay? Looks a little ill-conditioned, but I get to that one in a second. All right? So, oops. So for example, if I want to get the eigenvalues and eigenvectors, the spectral components of that are encoded in the operation that gets my snapshot basis, I can just take the eigenvalues of S and eigenvectors of S. Here the eigenvalues, here the eigenvectors. Okay? The eigenvalues, if I want to, I can leave it like that, but that's time-stepping eigenvalues, so they would be on the unit disk. If I like it more in a continuous way, I have to take the log and divide through by delta t, and now they're in the half plane, like we used to it with or Sommerfeld techniques and so on. The eigenvectors have to be, these are not the eigenvectors. Remember, this is the small matrix S. These are just the coefficients for the basis to express the real eigenvectors of the big matrix. Okay? So these are the coefficients from this eigenvalue problem times the basis to express it in, and then you get the dynamic modes of the full system. Okay? All right. So here is the whole algorithm, and that one is a first shot, and I'm going to do a second round on top of that one. So given a snapshot sequence from 1 to n, sampled equispaced in time with delta t. Okay? As I said, we can let go of that one, but for now it's convenient. I'm going to break my snapshot sequence from 1 to n into two subsets. The first one goes from 1 to n minus 1, and the second goes from 2 to n. Okay? Lots of overlap. I just duplicate it and shift it by 1. Okay? Then I go for the least squares fit for that last row in the companion matrix. So the best way to do that is to take a QR decomposition of the first snapshot basis, 1 to n minus 1. And then bring that one over and hit it with V2. So that's the second snapshot basis. This is basically S inverse. Okay. Sorry. This is a least squares of V1 n minus 1 inverse. This one. Okay. And that one gives you the companion matrix. That's all there is. Okay. And then I go for the eigenvalues if I'm interested in eigenvalues. And then I map them back with the log if I want to. And then I get the dynamic modes as the eigenvectors of that small eigenvalue problem in the snapshot basis V1 n minus 1. Okay, that's it. Now, one thing that should give you a little bit of pause is that R inverse, because you always have to ask, is R inverse defined? Is R invertible? Well, this is the full rank. So I assume that all these snapshots are linearly independent. Okay? If you have experimental data and you run it for a long time, there could be redundancy. Okay? So in that case, we're going to fail right here when R inverse is not defined. Okay? So we replace this one not by the QR, the full rank least squares problem, but the rank deficient least square problem. We throw that piece out and we put in an SVD. Okay? So we take an SVD of V1 n minus 1. That gives us U, sigma, and V. And then we invert that one with a pseudo inverse. Okay? And the nice thing about that one is here, we can actually specify a cutoff. We look at the singular values just like Scott did before. We look at the singular values. We see how rank deficient our data matrix is. So if I have 1,000 snapshots, for example, but only 100 are good, and then it repeats itself over and over again, like vortex shedding behind a cylinder. You know, if you've seen one cycle and the second cycle, the third, fourth, fifth, and sixth don't give you any more information. Okay? So the data is not rich enough, it's rank deficient. You need to cut that thing off. Okay? This is the place to do it in the SVD. You look at the singular values, when they drop, that's where you cut. So even if you have 1,000 snapshots, you really distill only the 100 or 200 or whatever good ones and make it into the S tilde. Okay? So that's the sanitized version of the DMD algorithm. And that one works fairly robustly. Okay? So now we have the modes. Okay? We have the modes. We have the eigenvalues. The dynamics goes here. The last thing we need to figure out is, what about the amplitudes? Okay? It's not trivial. And the reason it's not trivial is if you have bad data here, especially with outliers, then the amplitudes are doing some crazy stuff if you're not careful. Okay. The way we get the amplitudes is by formulating a optimization problem. Okay. We're going to formulate the optimization problem to say, you know, what are the, we go back to our data snapshots, we have our modes, we have the time dynamics, okay? And then we ask the question, what amplitude distribution will get us back to our original data as close as possible? So it's like a matching thing, okay? And it's a square matching thing, and this is the optimization problem that you have to solve. It's square in the amplitude. A is the amplitude that later on goes on a diagonal, okay? And these are the matrices that go in. I'm going to skip over the details and just sort of explain it on a little bit of a bigger picture thing. So if you want to optimize this one, we want to minimize this one, okay? This is the solution. A is equal to P inverse Q. It's a quadratic programming problem, okay? But it's a trivial one. P is positive definite, nice and convex, nothing goes wrong here, P inverse Q. Okay? That one works most of the time for clean data that comes from a nice DNS or something like that. If you go to experiments and you have outliers, this thing will fail. Okay? And the dirtier your data are, the more spectacular it will fail. Because if you have an outlier there, and the DMD algorithm, the way I presented it so far, is trying to make something out of it, it doesn't know what is an outlier or not. So if there's an outlier there that is in one snapshot really big, and in the next snapshot it's almost gone, okay, it interprets it as something with a big amplitude and a huge decay rate because it needs to be gone by the next time snapshot. Okay? So you get a big mess, the whole spectrum explodes more or less, and you get large amplitudes that mean nothing. Okay? So these amplitudes that come out of the A, it could be a melange of good amplitudes that are high for a good reason and good amplitudes that are just associated with outliers. So how do we sort out the good ones from the bad ones? So we do this one by using that same quadratic optimization problem, and we're going to add a sparsity promotion. So we say our amplitude vector that goes onto the diagonal later on has to be sparse. So that means we have to balance now something that gives us our data back, but we want to do that with as sparse an amplitude, with as few amplitudes as possible. Okay? And then something that is only contributing for one snapshot and has no contribution for all other snapshots gets automatically sorted out. Okay? We only want to have things that are valid over the entire data sequence. Okay? That's the general idea of that sparsity promotion. Okay? So this turns now into a L2 problem here and an L1 problem there. That's a mixed norm optimization, but there's routines now for this one. We use ADMM, the alternating direction method of multipliers, to do that. Now, the only thing we need to decide on is that gamma. And the gamma is a user-specified parameter that balance, that tells us, or tells the optimization routine, how much we value to get the data back and how much we value having a sparse amplitude vector. Okay? So if we pick gamma very small in the extreme 0, we only optimize the reconstruction. We get a very low reconstruction error, and we get a full diagonal. Okay? Very low reconstruction, but we even reconstruct the outliers. Okay? That's why we get a low reconstruction error. In the other extreme, if gamma is really high, we don't really care how well we reconstruct the data matrix.